Okay, good morning. And well, first I want to say I'm sorry for kind of the break in the lectures. I had ambition and intent to go to this conference and then also like provide some lectures, but I don't know. I just after the conference I was exhausted in that. I had a great time attending Python conference, PyCon, and going to these sessions and seeing kind of all of the latest things that are happening in the world of Python, which was very cool and exciting. But also, it was just kind of like mentally draining and taxing because you'd sit in these talks and these sessions and people would talk about what they're doing, and you'd go through like 6 to 8 hours of stuff, and then at the end of the day your brain is just kind of like it just felt like jelly. So anyway, I had a great time, but yeah, didn't post anything here. So I posted a video from last year regarding kind of an intro to SVM, and there's another part because in that video I didn't get through the entire slide deck, and so there's a second part covering kind of like nonlinear SVM things. It was in your homework, and basically there's kind of these two parameters that you can tweak, one being your gamma parameter and one being your cost parameter, and that affects the way kind of the boundaries are drawn. Beyond what you see in the homework, I recommend just kind of further fiddling around with those parameters yourself. Okay, so in the homework there was quite a few kind of images already in there, but just try putting in a few additional kind of different values to really get a sense of how gamma changes affect what the thing looks like, and how cost changes affect the thing. You can also kind of watch this video. I'm not going to have a view quiz associated with it. This is again from last year, and I provide view quiz answers in this, but I'm not going to require that. And we'll just kind of move on into today's topic, which covers clustering. But please do watch this and fiddle around with those cost and gamma parameters on SVM. Okay, what I want to look at today is on the topic of clustering. Okay, and so let's take a look here. Okay, so we are now going to just kind of start introducing unsupervised learning. So everything so far, I guess the first 7 weeks of our course has been supervised learning, in that you have training data and you have test data, I guess, test cases. And in the training data, there's answers, in that you have a value that you want to kind of target. So for like neural networks and stuff, there was a value that we wanted to predict. We wanted to say this set of numbers corresponds to the handwritten digit 8, or this corresponds to the handwritten digit 6. Or this was the test score. Or in the classification things, those are also supervised learning. There were answers, right? Predict Setosa, predict Virginica, predict this thing, and you could run it on your training cases, and you can see how well did it make that prediction. So that's called supervised learning, because you have answers, and so you can, quote, supervise the model in having this way to kind of check, did you do it like this is what it predicted, this was the correct answer, are they close to each other? Okay, and that's supervised learning. Unsupervised learning, on the other hand, is there's no correct answer. All right, so it's trickier because how do you measure how well you're doing? Well, you just say, you have to kind of look at different kind of metrics or different kinds of things, but there's not really an answer for you can say, well, this is where we're supposed to go, so I know we're headed in the right direction. Okay, so unsupervised learning, you have different kinds of ways to measure, like are things improving, and so one is kind of a measure of like internal variation, and so if you like in clustering, you want to kind of produce these clusters that kind of reduce internal variation or something like that. Okay, so unsupervised learning doesn't have target values. We're looking for kind of structure within the input values alone, and kind of broadly speaking, I would say the big broad categories of unsupervised learning are clustering and dimension reduction. Okay. So with clustering, the group is to create groupings of objects so that objects that are within the group are kind of similar to each other. So this is kind of the idea of reducing internal variation, that when you're within the group, it feels like everything or everyone is kind of similar to each other. There's not a whole lot of variation once you're within the groups. Okay, and obviously you have the entire data set, so you want to kind of create these different groups and these different clusters so that the objects within the group are similar. Right? Now, how do you define similarity? That's hard. We'll look at kind of one of the simplest methods, which assumes you have numeric values and you'll use Euclidean distance. Okay, so again, anytime you're using Euclidean distance, one of the first things you should think in your head is, I should scale all of my values so they're on the same kind of scale. Okay, I should normalize so anytime you hear Euclidean distance, because obviously if you're measuring distance, in centimeters versus inches one way, and the other way you're doing pounds versus kilograms or something, things are going to be wildly different. So Euclidean distance, think of like, I should scale everything. Okay, but obviously it's much more than just numeric values and distances, but clustering is helpful for grouping similar products together. Every time you go shopping, just with uncanny ability, it's almost, we take this for granted now, but you click on one product and then you're counting on like Amazon to present like other products that are similar, and you can start like looking, and like this is how you now search for like which, I don't know, whatever thing am I going to buy for myself, right? But also like if you've ever done like a Uber pool or something, it's trying to group similar passengers together so that, when the driver has to pick up multiple people, it's not going to be like taking them to the other side of town, right? So things like that. And so we'll look at, today we'll introduce k-means clustering. This is a very simple clustering algorithm. We're going to define objects being similar to each other by using Euclidean distance. Despite the letter K being common to both k-means clustering and k-nearest neighbors, are very, very different algorithms. For some reason, students sometimes get these mixed up, but I think it's just because of the letter K, but I don't know. So k-means is unsupervised. K-nearest neighbors is supervised. It's the classification method. K-means clustering, you'll see, is iterative, and k-nearest neighbors, there's no iterations. You just have your test point and count distances. Okay. As far as k-means clustering goes, your clusters are defined by centroids, okay? And the centroid is just the mean of the points that are assigned to that cluster from a standpoint mathematical formula. You can write it out like this. This makes it more complicated than it actually is. Just basically, the centroid do these points, what points belong to the cluster, and then what's the mean of those points, okay? Here, in order to get it to work, you say, all right, I've got this variable z. It's a 1 if it belongs to the cluster. It's a 0 if it doesn't, okay? And then so in the numerator, you take the product between z and x. So basically, you just get x for the values that belong to the cluster. It's 0 for everything else. And you divide by the sum of z, which is the sum of how many points belong to the cluster. Okay, and this is how the algorithm works. Is one is, I guess, step 0. Determine how many clusters you're going to search for. This is a non-trivial task. And then step 1, and this is depending on which source you read. Step 1 may or may not be this thing. Here I write number 1, randomly assign points in your data to each of the clusters. That's one way to do it. Another way is you just randomly pick centroid locations. Doesn't really matter, okay? But then once the values have been assigned to a cluster, you're going to calculate the centroid of each cluster. And then once you calculate your centroid, you're going to reassign values to the centers or to clusters by associating values to the nearest centroid. And then you iterate back and forth between steps 2 and 3 until you reach convergence. Convergence is reached when no values are reassigned. Okay, so this is your alternative initialization method. You can just randomly choose k observations from the data set and use those as your initial centroid locations. So, and then you just kind of proceed as usual, reassign values to clusters, recalculate the centroids, and you just go back and forth. Reassign points, recalculate clusters, or centroids. Yeah, I wrote, so because clusters are assigned using Euclidean distance, normalize or scale the values. All right, that's yeah, anytime you have Euclidean distance. Okay, so here's a very simple data set. I've got 8 points, and we're going to say, hey, we're going to search for 2 clusters. So visually, this seems stupid because obviously you have a cluster down here and a cluster up here. So anytime there's like a machine learning algorithm or something that you want to kind of try out or test, one thing I recommend doing every time is come up with a toy data set where you, the human, intuitively know the answer of like what it should result in, and then see if the machine learning algorithm is able to produce that, okay? To produce the results that you would expect. And if it does, at least you have a baseline level of, okay, it seems to be working. And if you try to run it and you're getting something totally wrong, then you know something isn't working correctly, okay? So here's a very, very basic thing. And we can just see, like, if I cluster these ones down here in the lower left should be in a cluster, these ones in the upper right should be in a cluster. And if we don't get that result, then something isn't working correctly, okay? Okay, let me give you your first view quiz answer, which is the letter A. A as an apple. Okay, so step 0, determine how many clusters we're going to look for. We're going to look for 2. Okay, that, and then step 1 now is going to be randomly assign the points to a cluster. So I'm going to just randomly assign my points to a cluster, and I'm going to just do Z. And so here, can you guys see that? I got 1, 2, 3, 4, 5 assigned to the red cluster, and I got 1, 2, 3 points assigned to the black cluster. Okay, those are the default colors that R chooses. Cluster 1 is usually colored in black. Cluster 2 is usually colored in as red. And so, so this is what we have. We're going to say, okay, let's find the centroid of cluster 1, the points in black. Let's find the centroid of cluster 2, the points in red. So what do I have? I got 0, 0, 1, 1, 4, 4. Okay. For cluster 1, 0, 0, 1, 1, and 4, 4. So I say, okay, what is x1, 0, 1, and 4? The mean of that is 1.667. Okay, x2, I also have 0, 1, and 4. The mean of that, 1.667. For cluster 2, it's these 5 points. And I can say, all right, I have 1, 0, 3, 4, 3 for x2. 1, 0, 3, 4, 3. The mean of that's 2.2. For x1, I've got 0, 1, 3, 3, 4. Also, mean is 2.2. Okay, so my centroids are at 1.667, 1.667, and then 2.2, 2.2. You can also use dplyr to get your centroids. You'll get the same results. And so I've plotted the centroid. Centroid of cluster 1 is right here. Centroid of cluster 2 is right here. So we've determined the centroids of our points, and now we're going to reassign the point to the nearest centroid. And I'm going to do this 1 point at a time, just to kind of illustrate. So we'll look at this first point, and we say, okay, which cluster centroid is closer, black or red? Clearly the black centroid is closer, so this point will get assigned to cluster 1. Okay, then we go to this point. Which centroid is closer, black or red? Okay, black is closer, it'll get assigned to cluster 1. Okay, and we go through, and all 4 of these points get assigned to cluster 1. Then we look at these points, which centroid is closer, and all of them, the red centroid is closer. So they all get assigned to red. So that's one iteration. Next iteration, we say, okay, what is the centroid of all of the points assigned to black? What is the centroid of all of the points assigned to red? Centroid for cluster 1, 0.5, 0.5. Centroid for cluster 2 would be 3.5, 3.5. So these are the new centroids. And then we can go through and we can say, all right, let's reassign points to the nearest centroid. No assignments are going to change. And so we'll say it has converged. So indeed, the k-means clustering algorithm has correctly identified our 2 clusters here. Okay, here is another example. Here I generated data from 3 kind of clusters. This is, I think, multivariate normal. And I've got a center right here at 0, 0, a center, I forget what value this is, but this was the original data. And then we'll see if we can kind of identify 3 clusters. So when you start, all of the data is unlabeled. So it's just a big kind of mess of points. And so here I'm going to just randomly assign points to different clusters. So we've got black, red, and green as our kind of 3 colors here. And so I just randomly assign points to black, red, or green. And then I say, okay, for all the points assigned to black, what is the centroid? For all the points assigned to red, what is the centroid? For all the points assigned to green, what is the centroid? So when you do that, these are the means that you get, okay? And so they get kind of plotted right here. If you have a small data set, when you do your random assignment, it is possible that, like, if you only have 10 points and you say randomly assign them to black, red, or green, it is possible that one of the clusters doesn't get any points assigned to it or something, right? Right? Like if you're searching for a whole bunch of clusters or something, then you just have to just do like another random reroll and do another random assignment. And it's also possible that after you find the centroids and you assign points, like things don't get assigned to a cluster. That's, I would say, rare, but it could happen. So here are my 3 centroids. And just kind of by coincidence, you can see, you know, the red and black centroids are very, very similar to each other. We got 0.086 and 0.025 and 0.037 and 0.025. Whereas the green one's a little bit different, 0.259. So it's offset a little bit. But so anyway, here we're going to assign all the points to the nearest centroid. And so you can see, because green is the rightmost and red is the leftmost, basically everything to the right is going to get assigned to green. Everything to the left will get assigned to red. And then there's only going to be a few points where the black dot, which is kind of underneath the red and green dots, only a few points will get assigned to the black dot here, okay? And that will be kind of like the points in the middle between red and green, if we can see that. And so, so after we reassign all the points to the nearest centroid, this is what we get. Let me zoom in a tiny bit. Okay, so so you can see these got assigned to green, these got assigned to red, and just a few points. Like for this point, we say which centroid is the closest, and between red, black, and green, black was the closest. So just a few points get assigned to black there. Okay, so now we say, okay, given all of these points, what is the centroid of everything in green? So probably somewhere around here. What's the center of everything in red? Probably something around here. And what's the center of everything in black? Probably something around here. And so we reassign or recalculate the centroids, and these are the new centroids. Okay, so this is the centroid for green, centroid for red, centroid for black. Okay, and now we reassign points to the nearest centroid. So this is stick, but you can kind of draw like a line between black and green here, and then have draw like a midpoint line. Okay, so imagine we've got this line that connects black and green here, and then we've got to kind of go halfway through here, and we want to go a little bit perpendicular, right? And so this is going to kind of be the boundary between black and green. Everything over here, green is going to be closer. Everything over here, black is going to be closer, right? Similar over here, you draw a line that kind of connects red and black centroid halfway, somewhere around there. And then perpendicular to that, you got some kind of boundary around here. Everything over here, red is going to be closer. Everything over here, black is going to be closer, kind of like that, right? So just imagine a line kind of right there, and a line like that. You know, we'll reassign points accordingly, and this is what we get. Okay. All right. So now that we've reassigned the points to the nearest centroid, we will recalculate the center. So given all of these points in green, where's the center? So we can see the centroid is going to move over that way. The centroid will kind of move over here. And for all of these ones, probably the centroid will move up to somewhere around here. So we do that. And then we recalculate, reassign points, okay? And so again, midpoint, so probably these points will get reassigned. These points will probably get reassigned as well. So the transition from here to here, you can see the kind of these points over here and these points over here get reassigned. And then we recalculate the centroids, and then we reassign points, recalculate centroids, reassign points, and this is kind of where we end up. So starting from here, recalculate, reassign, recalculate, reassign, recalculate, reassign, recalculate. Okay, and I think that's the final kind of thing. The coloring here, when you by coincidence, these ended up in red, these ended up in black, and these ended up in green, which aligned kind of with our original clustering assignments. But that's completely arbitrary, right? Because if you have 3 labels and you just say, hey, here's 3 groups, one person might call this group 1, group 2, group 3, and someone else might call this one group 1, group 2, group 3, or something, right, like that. So the it doesn't really matter if we've labeled this one the red cluster or the green cluster or the blue cluster or the purple cluster, as long as kind of all of the points that are in the same cluster are kind of in the same cluster, that's fine. Okay. So this is the result of k-means clustering. If you compare that to the original data, there's a couple kind of like things, like this point was red and this point is black, but after the k-means clustering, this point is black and this point is red. That's fine. The k-means clustering just says if you're using Euclidean distance, this point is actually more similar to this cluster, okay, than it is to the other ones, and I would agree with that, okay. But that's that, okay. There is a function in R called k-means, and this is what you get. So again, in your homework, you'll have to kind of code things yourself. But yeah, in R and in real life, you would not code it yourself. You would just use some of these already existing things. So k-means, we said, hey, search for 3 clusters, and it did it. And here you can see, yeah, you know what? It decided to call this one red and this one green over here, and that's fine. And if you run it again, you might get different results. Okay, let me give you your second answer, which is the letter B. B is your second answer. And so, yeah, running k-means clustering in R is very simple. You just call k-means and how many clusters you're searching for. I'm going to say we're going to search for 3. And so here I'm going to just plot my data, color the points by their resulting cluster assignments, and so we end up getting that. So what is k-means clustering doing? What it's trying to do is it's trying to minimize the sum of squares within a group, okay? So the within group sum of squares is calculated as the sum of squared distances from each point to the centroid of the group to which it is assigned, okay? Whereas the total sum of squares is equal to the sum of the within group sum of squares and the between group sum of squares, okay? So kind of like, I feel like we see this a lot, like in ANOVA, right? You have within sum of squares in between. Are you taking ANOVA right now? Or design of experiments or whatever? Okay. But you also learned it in linear regression, right? Within model sum of squares and residual sum of squares. It's all the same, right? And you got your total sum of squares. And the idea is, like, so remember that super simple example we started off with. We had kind of these 8 points. So the total sum of squares would be like, you'd have this, the centroid of everything would be like right here, and then you'd say like, okay, what is the distance to like these are your distances, and what are your squared distances? That would be your total sum of squares, right? So you take each of these things, and technically you could like draw a square, take each of these things and draw a square, and then take the total area. Okay, and then after you've got your cluster assignments, however, you have we have this cluster here, and then now we have these distances to here. So you can see like these squared distances are like much smaller than that, right? So this would be kind of like your within sum of squares, and then your between sum of squares would be from the centroid to the original kind of grand centroid or something. Okay. So anyway, k-means clustering, when you look at the results of k-means clustering, it computes your within cluster sum of squares. So it'll say, okay, within the cluster, what is the sum of squares? And then it will give you kind of the leftover. The leftover would be the between sum of squares, and that accounts for 86.2%. So this is kind of like your R squared value. Okay, I hesitate to say that because it's not like a regression type of thing, but the concept of like the sum of squares accounted for by the model divided by your total sum of squares, I think we can call it like an R squared value. And that's basically this. Okay, so we're getting like 0.862. And just like other regression models and things like that, you can always kind of bump up your R squared by adding more terms and making your model more complicated. Okay. So let me show you just kind of what happens. So here, this is what happens when you only have 2 clusters. Okay, with only 2 clusters, my R squared drops to 69.6%. And we can just see the plot looking for only 2 clusters. It just says here we have points over here and cluster over there, right? And so the points kind of in the middle got split between 2 clusters. On the other hand, if you say look for 4 clusters, you kind of get different results, right? So if I said search for 4 clusters, this is one partition that results. Okay, we end up getting 4 clusters like this. When you say one thing about k-means clustering is that it is subject to randomness, because your initial step is to randomly assign points to different clusters. And so depending on your initial assignments, then you can end up getting different clusterings. Okay, it's kind of like if you had to like group, I don't know, characters, movies, or any products together or something. If somebody kind of like predefines a few like archetypes or a few kind of starting categories, then you're going to end up gravitating towards those, or like forming clusters around that. Someone else might have a different set of kind of things, right? So, or I don't know, like music, right? So depending, like if you open Spotify or something and you have these different genres and these different, you have these different playlists, and basically playlists are clusters of songs, right? They're trying to like find similar songs. And so depending on who curated that thing, you have like certain songs might end up in one thing versus like a different streaming service. That same song might end up in like a different kind of playlist or something, right? Like, so like, because you have these, I don't know, however many things you have. So if I just kind of rerun k-means clustering with 4 clusters, you could end up getting different results. So this is another kind of split. So here, interestingly enough, you have a cluster over on the right, cluster on the left, but the center cluster, or the points in the middle, got kind of clustered, like separated, partitioned vertically, versus over here they got partitioned this way. Again, ignore the actual color themselves, just the structure of like, this is a cluster, this is a cluster, this is a cluster, and this is a cluster. And so that could happen. Here's another one where I just ran it again. And so you can kind of see it, like we're bouncing around between like, how are we splitting up some of these points and stuff? And that could happen. This is an issue with unsupervised learning, is that you don't have an answer, okay? Like, just imagine getting this impossible task that you are now in charge of all the playlists at Spotify, and then they make this weird rule that says every song can go only into one playlist, okay? Like this, once you assign it to a playlist, it can't go into any other thing. And then they say, all right, go ahead and make all of the playlists. That's like an impossible thing. And if different people have the job, even if they're both experts in this thing, you're going to get different results. And that's basically like, here we said, hey, look for 4 clusters, and you're getting different results. Is one more correct or less correct than the other? Well, we can kind of measure it using this between sum of squares number, and we're like trying to get something a little bit better, but again, you're not necessarily going to get great results. Okay, how many clusters should you search for? This is kind of an impossible question to answer, because you can always segment the data into smaller clusters, and if you do that, you will always eke out a little bit more, quote, R squared value, right? You can always reduce your within sum of squares by searching for even more things. So selecting an appropriate K, one approach is you can just try running it multiple times. And if multiple runs converge to the same cluster assignments, then if these multiple runs kind of converge to the same answer, then that's like a good sign. That's still not necessarily the correct answer. I guess to kind of compare how impossible of a task this is, or how difficult of a task it is, it'd be kind of like asking, like on the census data form, okay, like when you fill out the census, how many race or ethnicity categories should there be? Okay, this is a very tough kind of question, right? And so, if you go back several decades, it was basically either white or non-white, okay, person of color, and then you could say, okay, well, maybe we can have more categories, and you can say white, black or of African descent, Asian, or Hispanic, Latino. There's how many things, and then even so, like for me, I would say Asian, and then but that could get further divided, right? You can have East Asian, South Asian, Southeast Asian. You can split that, even like, and then among East Asian, that can get further divided into Chinese, Japanese, Korean, and even among, like, once you select like Chinese, that could get further split into even kind of more and more things. And so at what point did you say, all right, I think we have enough categories that it's, again, kind of an impossible thing to just say this is the quote correct number of clusters. You know, this strategy of kind of like trying out multiple runs and seeing what you have is one approach, but again, not necessarily always correct either, right? So here, what I've done is I've written a double for loop, which is always kind of advised against, but this is just for kind of illustration. Here I did search for k equal to 2, k equal to 3, k equal to 4, up to k equal to 10, and then within each of those things, I said run it 20 times, and let's see what happens. And so this is kind of our measure within sum of squares. So with k equal to 2, it always kind of converges to the same result. With k equal to 3, it always converges to the same result. You can see the within sum of squares is always exactly the same with k equal to 3. But as you get higher up, so k equal to 10, depending on the run, sometimes our within sum of squares was 264, sometimes it was 277, one time it was 247, 232, 291. You're getting variation. When you do k equal to 10, your within sum of squares varies. And so here I say, okay, what's the average sum of squares when you have k equal to something, and how much variation is there? So k equal to 2, k equal to 3, we had no variation. At k equal to 4, we start having a little bit of variation, and then you get as you get more and more clusters, you get more and more variation. Interestingly enough, you get quite a bit of variation at k equal to 5 for whatever reason. Okay, and so this is what we end up seeing here. Okay, but so just kind of ignoring this first one with k equal to 2, which is clearly a bad thing. Looking at the data, we would look at it and say, yeah, there's probably 3 clusters. But again, as you select more and more clusters, you're always going to get kind of improvement as far as like reducing your within sum of squares variation. But again, if you did say k equal to 7, which clustering of 7 is the correct one? It's hard to know because every time you run it, you get slightly different results as well. So so here, I said we see big drops when we go from k equal to 2 to k equal to 3, but after k equal to 3, sum of squares does decrease, but not necessarily at a rapid rate. But anyway, that's what you end up getting with k-means clustering. So so this is kind of the beginning. We'll look at k-means clustering after we apply like what do you call it? A kernel transformation. We'll take a look at that on Friday. But we'll go ahead and wrap things up here. Let me give you your last view quiz answer, which is the letter C. C as in cat. C. Okay, so we'll end things here, and we'll see you on Friday.